couple of specific interpretations directly related to the 1103 lab. The force versus position graph, trapezoid on the force versus position graph has F naught, FF, your two graph altitudes, F bar, your average graph altitude. Why do I call these things F's? Because they're measured in this direction, and that's a direction in which force is plotted. And the change in position here is delta x, which we will interpret, of course, as a change in position. Now, assuming that this represents a force and a displacement that are along the same line, the area of this trapezoid is the average graph altitude times its width, which is F bar times delta x. What's that represent? F bar delta x represents the work done on this delta x interval. Okay? What's the slope and what's it represent? Well, slope is the rise divided by the run. The rise is, well, the rise is from the vertical change in position from here to here. So it's the displacement from here down to here. So we could even depict it. We could draw a little triangle here. Here's the rise. Here's the run. The run is, of course, delta x. The rise is the change in the value of the function as you go from here to here, which will be the final value minus the initial value. So the slope, it has all these, well, slopes are represented by every one of these expressions. Okay, what does the slope represent? Well, it represents the change in f divided by the change in x. And the average rate of change of A with respect to B is change in A divided by change in B. Okay, corresponding changes in A and B. Okay, well, here clearly we have a change in F that corresponds to a change in X, and if we interpret this as an average rate of change, it means it's the average rate of change of F with respect to X. Well, there's even a little more to this. Let me get my fancy colors out again. If we take this to a limit, if we shrink this down towards 0 and take the limiting value of this average rate of change, we get the instantaneous rate of change. So the limit, average rate of change approaches the instantaneous rate of change, and we're talking about a rate of change of f with respect to x. That's just the derivative of f with respect to x. Go back to the way the derivative was defined. Okay? That's an idea you need to sort out. So, this slope would be an approximation to the derivative of f with respect to x. Of course, we know that the derivative is related to slope, but do we understand it in all this context? Well, that would be rare for somebody who's had a year of calculus. But you're in a position to understand it, and you need to understand this. Another graph, we have potential energy versus position. Okay, so we have some initial potential energy, some final potential energy, the left and right graph altitudes, and delta x here. Well, reasoning similarly, using the same properties as before, the area is going to be the average potential energy multiplied by delta x. How do we get the average of the potential energy? The graph is a straight line. It would be the potential energy at the midpoint, which is easily seen to be the mean of this potential energy and this potential energy. To get that, we add the potential energies, divide by 2, and then multiply that And that gives us the average graph altitude multiplied by delta x. That's the graph width. People always want to subtract the initial potential energy from the final, meaning that they're not thinking of the meanings. Because subtracting gives you this, and multiplying this by the width doesn't give you the area, does it? Okay? Now, in this case, the area represents nothing important that I know of. Just something's totally not important in physics. As I said previously, the area doesn't always have a significant interpretation, and this is one of those cases where it doesn't. However, the slope does. Slope is the rise divided by the run. The rise is what? Well, it's a change in the potential energy. The run is delta x, so you have the change in potential energy divided by delta x. Okay? Now, assuming this represents potential energy for some conservative force acting in the x direction, either positive or negative, that change in potential energy is what? Now, change in potential energy is equal and opposite to the work done by conservative force. Okay? Which means the average value of the conservative force multiplied by delta x. Okay, well, that's exactly what I wrote here in my numerator for my delta PE, going back to the definition. And again, I nag and urge that you do not think of potential energy as mgh. I have people that make the tragic error of using that to find the potential energy in electric and magnetic fields, where it doesn't even remotely apply. And next week we're going to talk about gravitational fields as we move significant distance away from the Earth. You can't use mgh even for that field. It's only one very limited application. It's an important application, but it's limited. It's not a definition of potential energy. This is the definition that we use for potential energy. It applies to potential energy in any situation. We can give another definition in terms of integrals, and we will, but conceptually, this is the definition that we're using. Anyhow, okay, so this is, well, I mean, it's the average rate of change of potential energy with respect to position, but that's just equal and opposite to the conservative force times change in position over delta x. And of course you have the change in position delta x here and here, divides out, you get that's equal and opposite to the conservative force. So that's the force you might exert against the conservative force. If you want to lift something, you got to exert that force against gravity, against the conservative force. Okay, so that the slope represents the negative of all the conservative forces. Negative average of all the conservative forces, where the average is taken over that interval delta x.